Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes, and we are talking about the metal joining processes. So, basically we will focus on the fundamental aspects related with the metal joining. So, as I said last time, we need to talk about the welding positions. These are the positions in which the welding is performed. The one is called flat, represented by letter F, and it is the horizontal position. The plates are kept horizontally, and then the joint is made like this. Then there is a horizontal welding represented by letter H, and here the plates are to be joined in vertical plane, and the joint is made horizontally in a vertical plane. So, the plates in vertical plane, but the joint is made horizontally, while in case of the vertical welding represented by letter V, the plates are also in vertical position like the horizontal welding, but the direction of the welding is also in the vertical plane. So, it is in vertical direction, vertically up or down movement, both any of the two can be used, but the plates in vertical plane and the welding direction is also vertical. So, that is vertical welding. And then overhead, which is very commonly used, which is very difficult position for the welding purpose. So, in this case basically like this is the top plate, and another joint is to be made in this way by depositing this fillet. So, this is the kind of overhead position of the welding. This is more difficult and requires very close control over the heat input and manipulation of the molten metal, so that it can be placed properly at the place where desired. Similarly, the control of the heat input as well as proper control of the molten weld pool is also needed in case of the horizontal and the vertical welding, because the molten metal will be placed in a vertical plane, so which will have tendency to fall down. So, maximum tendency to fall down is observed in case of the overhead welding, thereafter in vertical welding and horizontal welding. So, very close control over the heat input, molten metal, and skill of the operator. These factors play an important role in successful welding in vertical as well as horizontal and overhead positions. So, if we see like in case of the fusion welding processes, we need to for fusing the surfaces, we need to supply heat at the fixed surfaces. So, this heat can be used, this heat can be fed through the different sources of heat, which may be in form of flame like in gas welding, it may be in form of the arc like in arc welding processes, or it may be like resistance in case of electrical resistance heating or resistance welding processes, and then it may be in terms of the laser beam or electron beam in case of the radiation being processes. So, the heat is delivered to the fixed surfaces of the plates to be welded, and the melting of the fixed surfaces results in the metallic continuity and after the solidification of the weld metal. So, in this situation where just the fixed surfaces are brought to the molten state and thereafter solidification results in metallic continuity without addition of any filler metal, this kind of the weld is called autogeneous weld. Normally like the gas welding of the thin plates, TIG welding, plasma welding of the thin sections, laser and electron beam welding, all these are the processes wherein no filler metal is added. So, in this situation, whenever the solidification of the weld metal takes place, the solidification occurs. Say this is in this situation where the fixed surfaces have been brought to the molten state. So, it will have basically the number of unmelted grains, and molten metal is also of the molten metal is also of the same composition. So, these partially melted grains act as a nucleant, and the molten metal due to the loss of heat from the weld pool, the atoms starts getting deposited over these partially melted grains directly, and so the growth of the grains starts, and in this case no nucleation is needed because partially melted grains of the same compositions are already present. So, in cases where the base metal is just brought to the molten state and then solidification occurs just directly by growth approach. So, this is called epitaxial solidification, and gradually the entire amount of the molten metal is consumed by the growth of these grains during the solidification. So, it does not involve the typical steps of the nucleation and growth. So, the in all those cases where just the base metal is melted, or even if the filler metal is a filler of the same composition is added, then also the epitaxial solidification is observed. While in other cases where the composition of the filler metal is significantly different, there the conventional solidification is observed, wherein like say this is the base metal and the weld metal produced by adding the filler metal from outside. So, this is completely different from the base metal, and if it is so, like the crystal structure is different, metal is different. So, that will be leading to the first nucleation and then growth steps for completing the solidification. So, this is called the solidification wherein the nucleation and grain growth both are involved. Is in case of the, so this is what is the role of the heat in the fusion welding. In addition to the in addition to the fusing the fixed surfaces, heat also evaporates the moisture if it is present at the surface. So, the moisture is taken off, as well as the, if oxides are present, then these can be broken down and decomposed in course of the heat application of the heat, and then the melting of the fixed surface is also facilitated with the application of the heat. If we consider like the solid state joining processes, wherein the metal pieces to be joined in the solid state. So, under pressure the two are brought very close to each other, so that the fixed surfaces touch each other very firmly, and the metal to metal contact is established through the deformation of the peaks and valleys at the surface. So, like the peaks and valleys are present at the surface like this. So, peaks and valleys from both the sides will be getting deformed at the interface and will be leading to the complete metallic intimacy. So, the role of the pressure here basically it involves the use of the force or pressure, so that the required deformation, whether it is micro level or the macro level deformation, can be achieved. Micro level deformation is used in case of the ultrasonic welding processes, while a macro level deformation is used in the case of the friction welding processes. In addition to that, adsorbed gases, all gases, all the surfaces will have some of the adsorbed gases present at the surfaces. So, adsorbed gases are disrupted basically with the application of the pressure at the surface. Oxides oxides are fractured with the application. Oxides are fractured due to the micro level deformation which will be occurring at the surface. So, all these things will be increasing the metal to metal contact between the components to be joined, and once if it is there, then we will have the metallurgical continuity. If the two components are kept under pressure for certain time, then the metallurgical bond is established. So, the breaking of the absorbed disruption of absorbed gases, and the fracture of the oxide layers present at the surface is mandatory for having the direct metal to metal contact between the components being joined in the solid state. So these are these were the different kind of the things which are realized with the application of the pressure in the solid state. Joining processes like friction welding, ultrasonic welding, explosion welding, and another solid state welding process is the diffusion one, where the diffusion the two surfaces to be joined are kept in firm contact, metal to metal contact with each other under pressure in the vacuum environment. Normally the vacuum is of 10 to the power minus 3 to 10 to the power minus 5 torr, and under these conditions direct metal to metal contact existence. So the diffusion starts from one side to another due to the concentration gradient of the elements across the interface, and this eventually forms the grains across the interface, so that in turn leads to the metallurgical continuity. So that heating is important to facilitate the diffusion, since the diffusion is a slow process, so it takes time. So we need to provide enough time so that diffusion can occur across the interface. Normally 30 minutes to the 2 hours time it takes to have the kind of the metallurgical continuity across the interface, and the temperature can vary to the range of like say 0.5 to 0.6 times of the melting point of the metal in Kelvin. Another important thing is here pressure. Pressure is normally plays a big role. Pressure should not be too high, otherwise the macro level deformation at high temperature can occur. So that the pressure is normally like say 2 to 10 MPa pressure is normally used in order to have the diffusion bonds. Various approaches are being tried in order to increase the effectiveness of the diffusion bonding process through the pressure pulsation or by putting in the soft material interlayer, so that the diffusion and the metallurgical connectivity, means the metal to metal contact, can be enhanced through the use of the pressure pulsation, increasing the pressure, as well as the use of the a soft metals interlayer like the copper, nickel, or the silver or the common the metal systems which are used for this purpose. Now as I said, for the fusion welding what we need to supply heat. So there are various heat sources, each differs in terms of the energy density which is available with them, and it plays a big role like energy density which is delivered by the different processes like gas welding, arc welding, resistance welding, then laser beam welding, and electron beam welding. These processes differ with respect to significantly in terms of the energy density that they provide. So energy density, if we measure in terms of the like joules watt per mm square, then for the gas welding it comes out to be the 10, for arc welding it is 50, for resistance welding it is 1000, for laser welding it is 10,000 and 9,000, and for electron beam welding it is 10,000. So for facilitating the fusion, minimum 10 watt per mm square energy density is needed. So what is the role of the energy density in facilitating the fusion, and the amount of the heat which is required to melt? For that we need to see if we have here the time on the axis scale and energy density on the y scale. Then what we will see here is that like say when the energy density is low, it is required to supply the energy or the heat for a longer time as compared to the case when the energy density is high related with the process. So for short time we need to supply the energy. So this is for high energy density process, like laser beam or electron beam, and this is like say the low energy density process like arc welding or the gas welding. From the fundamentals of the heat transfer, we know that if the heat is delivered for longer period, then lot of heat will be transferred to the underlying base metal, and in that case it will require larger amount of the heat as compared to the case when the heat is delivered for shorter period in order to ensure the melting. So, if we see here like these are the plates to be welded. If the energy density is high, then to ensure the melting very shorter to ensure the melting, the energy is to be delivered or heat is to be delivered for a shorter period of time. So, in that case the dissipation of the heat to the base metal will be less as compared to the case when the same kind of the combination subjected to the lower subjected to the delivery of heat using the low energy density process. So, this is a high energy density process and the low energy density process. So, weld it requires lot of heat to be delivered to the base metal because it takes longer time. So, lot of heat will be dissipated to the base metal. So, if we compare the net heat input for the amount of heat that is required to be delivered to the base metal for low energy density process is much more as compared to the case when the high energy density process which is used. So, H net, if we see the net heat which is required for ensuring for facilitating the melting in the two cases, H net will be more for the low energy density process as compared to the case when the high energy density process is used. So, the time for which energy is delivered or heat is delivered to the base metal matters a lot in terms of the amount of heat that is required to be delivered, because a lot of heat is dissipated to the base metal and that will be causing the number of effects which may be in terms of so increasing the H net simply increases the weld cross sectional area, it will increase the heat affected zone size, it will increase the thermal damage to the workpiece in terms of the like increasing the residual stresses, increasing the distortion tendencies. So, all these problems will be more. So, it is always good that the joint is made using the as less heat as possible for facilitating the fusion, and for this purpose high energy density processes offer the much better results in terms of the thermal damage to the workpiece which will be taking place due to the application of the heat. So, if we see here the energy density actually energy density varies with the varies as we move away from the center, like say this is the center of the heat source. So, the energy density increases and then it decreases as we reach away. So, on moving away from the center of the heat source, energy density decreases rapidly. So, these are the locations if we see. So, at the center of the arc we have much higher energy density as compared to the case when the outer region of the heat source. So, this is what we can directly calculate, like the energy being delivered maybe in terms of the joule and the area over which it is being delivered. If we consider this area or this larger area, in both the cases the energy density will be different. So, energy density in joule divided by the area, that is what we can calculate in mm square. So, we will be getting like area pi by 4 d square as per the location of the interest d we can select. So, this is what will be telling us the energy density will be maximum at the center, and it will keep on decreasing on approaching from the center towards the surface of the heat source. Like it may be flame or it may be arc. Then coming to the some fundamental aspects, like people have identified the amount of heat required for melting can be given by the like relationship Hm. Heat for the melting purpose can be obtained through the simple relation like K multiplied by Tm square. So, Tm is the melting point in Kelvin, and the K is constant, and whose values the value of the K is given as 3.3 10 to the power minus 6 for while the value of the value of the Tm, the melting point for aluminium, like say in the Kelvin scale, is considered 930. For cast iron it is 1530. For copper it is 1350. For Inconel, one of the very commonly used commercial metal, it is 1660. For Mg it's low 940, and for nickel it's 1720. For low carbon steel 1760. For high carbon steel it is low, comparatively low, so it is 1650. And austenitic stainless steel say 1670. So, these are the lastly one for the titanium, which is much higher, like 2070. So, multiplication of the Tm, these are the Tm values, the temperature, melting point temperature in Kelvin scale for the different metal systems, and by multiplying this we can identify the amount of heat that will be required for the melting purpose. So, actually the amount of heat required for the melting purpose can be calculated using this, but we know that whenever we use any process, like whether it is arc or any other process, so we deliver some amount of the energy, like say some current and some voltage, but whatever energy is generated can be obtained say from Vi, but the same amount of energy is not converted into the heat. So, the part of the heat which is converted energy, the part of the energy which is converted into the heat is termed as the heat efficiency, and whatever is the amount of heat is available, only a part of that is used for the melting. So, amount of heat available and what portion of it is being used for the melting purpose, that gives us the melting efficiency. So, depending upon the process, the heat efficiency is influenced, while the melting efficiency depends on the process, as well as the thermal conductivity and the volumetric specific heat rho c, and like the thickness of the metal. So, all these factors which will be affecting the melting efficiency, means the proportion of the heat which is actually being used for the melting purpose, so that the joint can be obtained, while out of the given amount of the energy, what proportion of the energy is being converted into the heat, that gives us the heat efficiency or thermal efficiency of the process. So, normally if both are clubbed, like we call it as a thermal efficiency of the welding process, which is normally, like say for the different process it is different, like for the simple arc shielded metal arc welding process, this may be like 80 to 90%, but for submerged arc welding process this is 90 to 95%. For the gas tungsten arc welding process it is very low, 40 to 60%. For the laser beam it is further low, like 10 to 15%. So, depending upon the processes, the different thermal efficiencies are observed, wherein we deliver some amount of the energy during the welding, but only part of that is used for the melting purpose. So, remaining portion of the energy is wasted in different ways. Like say if you have to calculate the amount of the heat and the rate at which the weld is being made, uh, heat delivered during the welding is equal to the energy used for melting multiplied by energy used for the melting of unit volume multiplied by volume of the weld which is being made. So, if we calculate this, the energy is the energy required, U is the energy required for unit volume multiplied by the rate at which the weld is being made, weld rate, the rate at which the weld is being made, and so it is the volume of the weld, the rate at which it is being made, and for that U is the heat required for unit volume multiplied by AW is the cross sectional area of the weld multiplied by the speed of the welding, like say S. So, the speed of the welding, cross sectional area of the weld, and amount of the heat required for melting the unit volume of the metal. This will be giving us how the heat delivered is being utilized. So, if we are aware of the heat being delivered for the melting purpose during the welding, then the unit volume of the heat required for melting and the heat required for melting the unit volume of the metal, cross sectional area of the weld, and the welding speed. This can be used. So, any one if is not known can be determined, like the heat required for melting the unit volume of the material is a kind of property which can be obtained from the welding speed. We will be knowing the rate speed at which the welding is being done, and so from the setting of the welding current, welding parameters, we can obtain the amount of heat which is being delivered as well as from the thermal efficiency of the weld. So, like say neta multiplied by V, or say for the arc welding process, this will be giving us the amount of heat which is being delivered, then the unit amount of heat required for melting the unit volume of material multiplied by weld cross sectional area multiplied by the welding speed. So, if we know this, if you know welding speed, we can determine the weld cross sectional area. Now, we know that whenever the metal is melted during the welding, melting of the metal increases the temperature as well as brings the part of the metal in the molten state. So, this molten metal when it comes in contact with the atmospheric gases, when it comes in contact with the atmospheric gases like oxygen, nitrogen, hydrogen, etc. So, this interacts and forms their oxides, nitrides and hydrides. So, if these are having the density same as that of molten metal, then they will get uniformly distributed, and after the solidification these will be present as inclusions. And if this is the case when these gases have interacted or reacted with the molten metal. In the case when these do not interact, then these will be present as a gas pores, which is called porosity. So, if they interact, they will be leading to the inclusions, and if they do not interact, then they will be present as inclusions. So, it is important that we take care of the atmospheric gases properly during the fusion welding, and for that purpose the various approaches are used. These approaches are like a use of the molten flux, use of flux coatings, use of vacuum, and use of the inert or active gas cover or blanket around the arc. So, these are the approaches which are used. Use of the molten flux is used in the submerged arc welding process. Flux coating is used in case of shielded metal arc welding process, as well as in the flux FCAW flex core arc welding process, and then vacuum is used in electron beam welding process. And use of cover of the inert or inactive gas is used in case of the gas tungsten arc welding like inert gases, and gas metal arc welding PAW plasma arc welding also uses the inert gases. Then gas metal arc welding uses both inert gases or active gases like maybe CO2 or the nitrogen can be used, or here inert gases like argon and helium are normally used. For high quality welds, helium is preferred, while for commercial quality weld joints the argon is normally used, because argon is cheaper and cost effective as compared to the helium. Also the availability of the helium becomes an issue, because it is not that easily available, and the cost difference is huge, like maybe 4 to 5 times cost difference in the cost of the argon and helium. So, for most of the commercial purposes like the welding of the pressure vessels and where reasonably good quality welds are required, helium is used as a in shielding gas. Argon is used as a shielding gas, while helium is preferred for very high quality weld joints, because it is very costly and very high flow rates are needed when the helium is used. Now, apart from this, application of heat for the melting purpose results in the first is the fusion of the fang surfaces. So, this molten metal is created, then a joint near the base fusion boundary, like say this is the fusion boundary, this is the root, this is the reinforcement, this is the reinforcement, and so a fusion boundary, and the region near the fusion boundary is heated to the high temperature. It does not remain at room temperature, and this happens because of the thermal conductivity ability of the metal to transfer the heat away from the fusion boundary. So, that this rise in temperature actually changes the so then the region near the fusion boundary experiences the changes in terms of the microstructure of the metal and the mechanical properties. There is no particular pattern in which the structure and the mechanical properties will be affected. Sometimes it causes the softening of the metal, or it may also leads to the hardening. So, depending upon the kind of metal systems which are being welded, they may get hardened or they may get softened. For example, most of the steels in normal condition like annealed normalized conditions, they get hardened, while the precipitation hardened aluminum alloys as well as quenched and tempered steels both get softened. So, depending upon the kind of process and the metal system, the hardening and the softening can occur in the heat affected zone. So, it is irrespective of the weld metal quality, there is always the heat affected zone formation, and this the size of the heat affected zone may vary depending upon the kind of the heat input which is being delivered and the conductivity of the metal, thickness of the sheet, etc. So, it is always efforts are always made that HAZ size is as less as possible, so that these changes being experienced by the base metal near the fusion boundary are as less as possible. Now, coming to the arc welding processes, that this is one of the major category in the welding processes and which are extensively used. Like among the all metal well metal deposited, the shielded metal arc welding accounts for about 70 to 80% of the well metal volume. So, that is of the great commercial importance. Apart from that, submerged arc welding, shielded metal arc, submerged arc welding, and the electroslag welding is also used for the welding purpose. So, coming to the some technical aspects related to the welding, the welding processes, like there is one electrode, there is one work piece, like this, and there is one power source which may be connected to the electrode. So, power source will have positive terminal and a negative terminal. Depending upon the kind of polarity or the kind of type of current, it may use AC or DC. So, when AC is used, the polarity will keep on changing after every half cycle. So, accordingly the polarity of the welding arc will be changing, while in case of the DC we will have the freedom of choosing whether the electrode will be connected to the positive terminal or it will be connected to the negative terminal. When electrode is connected to the positive terminal and workpiece is connected to the negative terminal, it is termed as a DC reverse polarity. And otherwise, when the electrode is connected to the negative terminal and workpiece is connected to the positive terminal, it is termed as DC straight polarity, or this is also called as a DC EN, and this is termed as DC EP, DC electrode positive or electrode negative, or straight polarity or negative polarity. So, this is the case of the DC RP, reverse polarity or electrode positive. So, what is the importance of the DC EN or DC EP? We know that whenever there is welding arc, the more welding arc, the more heat is generated on the positive side and the less heat is generated on the negative side. So, means the electrode, if it is connected to the positive, then it will be termed as anode, and another one workpiece will be termed as cathode. So, in this configuration, whenever there is welding arc, the more amount of heat, like say the heat generated by the arc can be given by Vi. This is also termed as power of arc. So, whatever heat is generated by the welding arc, 2/3 of the heat is generated at the anode side, while 1/3 of the heat generated by the arc at the cathode side. So, in this scenario, more melting of the electrode will be occurring as compared to that of the base metal. So, this will be leading to the melting of the electrode at much faster rate than the base metal, but when we are so this may be good when the thin sheets or thin plates are being welded, but when we are working with the thicker plates. So, for welding of the thick plates, normally we prefer to go for the electrode negative and workpiece positive, so that more heat is generated in the workpiece side in order to ensure the penetration through the thickness of the plates, so that the required weld can be obtained. So, electrode DC EN is preferred when the high conductivity of the metal, greater thickness of the plates are being welded. So, the more amount of the heat being generated in the electrode side can facilitate the melting of the base plates. So, now I will summarize this presentation. In this presentation, I have talked about some of the basic aspects related with the welding positions and the role of the heat input in development of the sound joints, and how does the power density affects the amount of heat required for the welding purpose. At the same time, I have also talked about how does the energy density varies in the heat source, which is maximum at the center, and then it will keeps on decreasing away from the center with the so as we approach from the center to the surface of the heat source, it will keep on decreasing. We have also talked about the how the heat input being delivered or heat being delivered during the welding can be used for calculation of the the weld metal deposition rate, or how can we calculate the cross sectional area of the weld if we are aware of the heat being delivered and the welding speed. Thank you for your attention.